Welcome back. So last time we talked about root mean squared error, right? That one single number that's supposed to tell you how good your model is. But what if I told you that number isn't telling you the whole story? Today, we're going to crack that error score open and find out what's really going on inside. We're going to uncover the three hidden forces that are actually driving your model's mistakes. You've probably been there before. It's one of the most frustrating things in machine learning. You build this incredibly complex, sophisticated model, it absolutely nails the training data, like a perfect score. Then you show it some new data, and it just completely falls on its face. How is that possible? How can being smarter actually lead to a worse result? Well, the answer is hiding in plain sight, right inside that error score. You see, prediction error isn't just one thing. It's actually a mix of different forces, all pulling in different directions. And if we want to solve this paradox, we have to understand the anatomy of that error. Okay, let's get into it. Here's our game plan. We'll start with that smarter model paradox, then we'll dissect the error and meet its three core components. After that, we'll see how two of them are in a constant battle, and finally, we'll talk about how you can master that conflict to build way better models. So where do we even begin? We start with the blueprint. It turns out there is a fundamental equation in machine learning that lays out the entire plan for model error. And once you get this, seriously, everything else just clicks into place. The thing we're trying to understand is called the expected prediction error. You can really just think of it as the long-run average of the mean squared error we covered last time. It's the ultimate measure of that gap between reality, what we call y, and our model's prediction, which is y hat. And here it is, the big reveal. That total error you're trying to minimize, it's not one giant scary thing. It actually breaks down, beautifully, I might add, into three separate pieces: irreducible error, squared bias, and variance. So the most important thing to remember is that your total error is just these three things added together. All right, now that we have our blueprint, it's time to meet the three culprits responsible for our model's mistakes. Let's put each one of them under the microscope. First up on our list is the irreducible error. And, the name kind of says it all. This is the part of the error that, well, you're stuck with it. It's a baseline level of noise that no model, no matter how clever or powerful, can ever get rid of. So where does it come from? Here's the thing. It's not your model's fault. It's just the real world. It's the randomness that's naturally baked into the data. I like to use an archer analogy for this. The irreducible error has nothing to do with the archer's skill. It's as if the target itself is constantly, randomly shaking. Even the best archer in the world can't hit a bullseye if the target won't stay still. So the bottom line here is simple. Irreducible error sets the performance floor. It's a hard limit, the absolute best anyone can ever hope to do with this particular dataset. You can't model it away, you can't wish it away, you just have to accept it and focus on the parts of the error that you can control. Okay, culprit number 2, bias. Bias is the error you get when your model's assumptions are just too simple for the complexity of the real world. It's a stubborn, consistent kind of error, the difference between what your model predicts on average and the actual truth. This is the classic signature of underfitting. Let's go back to our archer. High bias is like having a crooked sight on your bow. All your arrows might land really close to each other, a nice tight cluster, but that entire cluster is consistently off the bullseye. Maybe it's always high and to the left. The model is consistently wrong in the exact same way every single time. And that really gets to the heart of what bias is. It's this fundamental mismatch between how your model sees the world and how the world actually is. If you try to model a complex curve with a simple straight line, you're going to have high bias. To fix it, you need a more flexible model, something that can actually capture the true patterns in your data. And that brings us to our final culprit, variance. Now, if bias was all about being too simple, variance is the complete opposite. It's about being too complex. Variance measures how much your model's predictions would change if you just trained it on a slightly different sample of your data. It's the error of being overly sensitive, and it is the hallmark of overfitting. For our archer, high variance is like having a very shaky hand. On average, the shots might be centered around the bullseye, but they are scattered all over the place. The model is unstable. Tiny little changes in the training data can cause its predictions to swing wildly. So yeah, variance is the error of instability. It's what happens when a model is so flexible that it starts to memorize the noise in the training data instead of learning the actual underlying signal. And the cure for high variance? Often, it's just a dose of simplicity.
Now, this is where things get really interesting. Bias and variance. They're not just two separate issues. They are locked in a constant battle with each other. It's a push and a pull, this constant tension. And honestly, this conflict is pretty much the central story of all of supervised learning.
And this right here perfectly illustrates that core trade-off. As you make your model more complex, say you go from a simple linear model to a really wiggly high-degree polynomial, your bias goes down. That's great. The model is more flexible, it can fit the data's true shape better. But at the exact same time, your variance shoots up. The model gets way too sensitive and becomes very prone to overfitting. This table right here, this solves the mystery we started with. Take a look at the extremes. A really simple model, it has high bias, and that leads to high total error. A really complex model, it has high variance, and guess what? High total error again. The goal isn't to get bias or variance to zero. The goal is to find that sweet spot, that Goldilocks zone right in the middle, with just enough complexity to get the total error as low as possible. So we understand the conflict. Now, how do we master it? Because this decomposition isn't just some abstract mathematical idea. It's a powerful strategic framework for building better models in the real world. If you only take away one thing today, let it be this. The goal is not perfection, it is balance. We are never going to build a perfect model with zero bias and zero variance. It just doesn't exist. We are simply trying to find the optimal balance between them that gives us the lowest possible error on new data. So here's how you can think about this strategically. First, just recognize that every single decision you make, the algorithm you choose, the parameters you tune, is a move you're making along that bias-variance spectrum. Second, and this one's a big one, you have to embrace the idea that sometimes making your model a little simpler, that is, injecting a little bias, can cause a huge drop in variance and lead to a much better model overall. And finally, always keep your eye on the real prize, the lowest possible total error. And that leads us to a fascinating and really powerful question. If accepting some bias is actually the key to reducing variance and making our models better, how do we do it in a principled, controlled way? How can we deliberately tune this trade-off? Well, that is an excellent question, and it's exactly what we're going to explore in our next explainer.